Can you recognize any message here? No, me neither. But it's there anyway. Today I will show you how to read message signals despite strong noise. And we are going to do a little experiment on that. Today we are once again dealing with an important fundamental in communication technology. But don't worry, we won't get into the theory of information technology. We are going to do a little experiment with a digital signal that we are superimposing with noise. By the way, on this topic, I can also recommend the video at the top right. And there are quite a few interesting videos on wireless communication on the channel. It might be worth subscribing. When we talk about the transmission of bits and bytes, we immediately have an idealized picture with zeros and ones in mind. In reality, of course, we use electrical, optical and sometimes also acoustic signals to carry the bits and bytes. In the experiment, we look directly at what a digital signal looks like when noise is superimposed on it. Then we determine the bit error rate to assess whether the signal could eventually be decoded. Without going into more detail now, I would like to refer to a classic work by Claude Shannon in this context. He was an American mathematician and electrical engineer. He is regarded as the founder of information theory, together with Harry Nyquist and Ralph Hartley, who also did fundamental work on it. I can recommend anyone who wants to dive deeper into the matter to study the papers of these engineering scientists. Maybe my video will make you a bit curious on it. Now we come back to our signals. I use a similar representation here as Claude Shannon. Here we have a signal source that emits a digital signal. Then we have a signal path where noise is added to the signal. In wireless systems, it is mainly the receiver's inherent noise that plays a role here. Depending on how large the signal-to-noise ratio is, the signal is more or less disturbed. And there is also a bandpass filter in the receiver that is smoothing the signals somewhat. And finally we have a demodulator that gives us the information bits that we originally sent. We would like to know what the signals on the signal path look like and under what conditions the transmission of our data can work. A little experiment should show us that now. The bit error rate serves as a criterion for the quality of the data transmission. And let's go! In our little experiment we have a digital signal here. Then we have a noise signal here. We can now superimpose these two signals. We can specify the signal-to-noise ratio here, and here we get the noisy signal. At 30 dB SNR it looks very good, as expected. You can see with the naked eye that the signal can certainly be correctly demodulated. Then we look at the signal behind the bandpass in our receiver. This is smoothing the signal somewhat because the high frequency components of the noise are suppressed. By the way, this is a digital filter with adjustable filter coefficients. I derived the filter coefficients from the SI function here. You could also experiment with the coefficients. What do you think? Write me in the comments. On the right we have the bit error rate that we get when we demodulate the signal to retrieve the bits sent. We now assume that our error correction can correct up to 10% errors. That means that as long as our bit error rate remains below 10%, we can transmit our information correctly. As expected, with a signal-to-noise ratio of 30 dB, we have a 0% bit error rate. Now we reduce the signal-to-noise ratio to 20 dB. Incidentally, we have a simple amplitude modulation here that is relatively robust. However, you can only transfer relatively small amounts of data with it. Higher modulation coding schemes, such as 64QAM, could transfer a lot more data, but we would certainly see bit errors here already. We try 10 dB SNR next, and we still don't see any bit errors, although the signal is already quite deformed. But apparently the deformations do not yet touch the threshold value that decides between 0 and 1. At 6 dB we then get a small bit error, but it always remains below 10%. One could still live with that. At 3 dB, however, sometimes the 10% threshold is exceeded. As users, we would perceive that as interruptions. At 0 dB, we then have the problem that the connection would break off because there are too many bit errors. Anyone who thinks that we have reached a physical limit here is wrong. In fact, there are ways to demodulate signals that are far lower than the noise power level. And this means actually receiving signals with a negative signal-to-noise ratio. The simplest way to achieve this is to repeat signals multiple times. The noisy signals, which of course all look different, are stored on the receiving side. And of course, the information content cannot be seen in a single signal. But we can now sum up the signals. And we do that in a second experiment. We look at the sum signal from 31 repetitions. And what can I say? With a signal-to-noise ratio of 0 dB, we have no bit errors. So let's go to a negative signal-to-noise ratio. At -3 dB, the transmission still works perfectly. Even at -6 dB, there is no problem at all. Even at -10 dB SNR, the signal still works wonderfully. However, we must of course consider that the 31 repetitions of our information naturally reduce the transmission speed by a factor of 31. That's the price you have to pay for the extra system gain you get with it. For instance, with a radio system, 10 dB more system gain could triple the range, at least in free space. That's not bad, isn't it? At -13 dB, we are already approaching the theoretical limit, and we can see that more bit errors are appearing. We often exceed the 10% limit. At -16 dB, the transmission channel would be unusable because the bit error rate is too high. It's a bit crazy, but it actually works. Using the sum of the repeated signals, we can save the wanted signal from the noise. Then we actually get a clean signal again, and we can demodulate it. But why is that? I mean, we certainly add up the noise signals, or not? If we add two signals with uncorrelated noise, then we actually double the noise power. This is for sure. But if our two information signals are synchronous, we double the voltages. And double the voltage means quadruple the power. This means that the more synchronous signals we add, the more signal-to-noise ratio we gain. In the case of 31 repetitions, that would be 10 times the logarithm of 31 equals 14.9 dB. Cool, right? If you want to overcome the intrinsic noise of a receiver, then you can also work with several receivers. The principle is similar to the one before, and the achievable transmission speed even remains the same. However, this method cannot reduce interference on the transmission path like the method before. But it's also a very interesting technology, because today you can, for example, integrate 1000 receivers on one chip. That would then increase the system gain by 30 dB. And that's quite a lot. Unfortunately, there is still a small problem with this technique. I said that the effect is based on adding up the voltage of synchronous signals. However, this means that the signals in reality must be fairly well synchronized. In our experiment, the synchronization of 0 bits means that the added signals are exactly in sync. This is technically not easy to implement if you want to work with signal repetition. Now let's do an experiment with a non-ideal synchronization. We assume that our 31 signals are allowed to shift in time by about 0.3 bits. We see immediately that the bit error rate is rising and often exceeds 10%. If we were to work with it, we would need better error correction, which would mean more overhead and thus a further reduction in the transmission rate. So, you see, precise synchronization is important. With a synchronization error of 0.7 bits, the transmission channel would be unusable in this range. The insights. We have looked at a digital signal in the time domain. And we have seen where the limit of the signal-to-noise ratio lies in order to be able to demodulate a signal. In addition, we have seen that a signal well below the noise level can still be demodulated. There are two ways of doing this. The signal can either be repeated several times, or the signal can be processed and summed up in parallel with several receivers. If you manage to add up a repeated signal synchronously, you can actually save a signal that is far below the noise level. And the clue behind is quite simple. With synchronous signals, the voltages add up, and with statistical signals, such as noise, only the power of the individual signals adds up. As a result, the signal strength grows faster than the interference when several signals are added together. Hope you enjoyed the video. Occasionally there will be more on the topic. Now stay tuned and don't forget to support the channel. See you soon in the coming episodes.